Now I'm going to be talking about masked Siamese network for label-efficient learning. So they propose masked Siamese network as a self-supervised learning framework for learning image representations. Their approach matches the representation of an image view containing randomly masked patches to the representation of original unmasked image. This self-supervised pre-training strategy is particularly scalable when applied to vision transformers, since only the unmasked patches are processed by the network. As a result, these masked Siamese network improve scalability of joint embedding architectures while producing representations of a high semantic level that perform competitively on low-shot image classification. This is the visualization of MSN representation. The first column, this column, which is the original image, but the second column is the image with 70% patched mask input to an MSN pre-training encoder to encode representations. So other columns, samples of a generative model conditioned on the MSN representations. Quality that vary across sample represents information that the pre-trained representation is invariant to. So we have the original image, we have anchor view, and then we patchify a mask. We give it to one of the network, but the network we use exponential, this moving average, and then we use the prototype in order to see the prediction. And finally, we use this to create the loss. So they use a standard vision transformer architecture as the encoder. And vision transformers first extract a sequence of non-overlapping patches of resolution n by n from an image. Next, they apply a linear layer to extract patch tokens and subsequently add learnable positional embeddings to them. An extra learnable token is added to the sequence. This token aims to aggregate information from the full sequence of patches. So one way is just mean pool averaging. Another approach is just using the one related to CLS token. And the sequence of tokens is then fed to a stack of transformer layers. And it's composed of a self-attention and a fully connected layer with skip connections. Self-attention uses an attention mechanism applied to the entire sequence of elements to update the representation. The output representation associated to CLS token is used as the output of the encoder. We now describe the proposed masked Siamese network, which combines invariance-based pre-training with mask denoising. So it first uses random data augmentations to generate two views of an image referred to as the anchor view and a target view. Subsequently, a random mask is applied to the anchor view while the target view is left unchanged. Similar to clustering-based SLSL approaches, learning occurs by computing a soft distribution over a set of prototypes for both the anchor and target views. The objective is then to assign the representation of the masked anchor view to the same prototypes as the representation of the unmasked target view. And we use a standard cross-entropy loss to optimize this criteria. So here is the no mask, but here we use random mask, and this is the focal mask. There are different masking strategies. So for the encoder, given a parameterized anchor encoder, Z sub I and M denote representation computed from the patchified and masked anchor view. Similarly, given a parameterized target encoder with a potentially different set of parameters denote the representation computed from the patchified target view. And we use similarity metric so Q denote the k-learnable prototypes. So these are k-learnable prototypes. Each one has dimension d. To train the encoder, the computer distribution based on the similarity between these prototypes and each anchor target view pair. And we penalize the encoder for differences between these distributions. More precisely, for an anchor representation, this is the anchor representation, we compute a prediction in a k-dimensional simplex by measuring just the cosine similarity to the prototype's matrix Q. And for L2 normalized representations and prototypes, this prediction, Pi and M, can be concisely written as a softmax. And of course, tau is here is a temperature, is a hyperparameter. And similarly, for each target representation, we generate a prediction by measuring the cosine similarity to the same prototype matrix, because the clusters are not changed. I mean, these prototypes are not changed. Note, we always choose tau plus less than tau to encourage sharper target predictions, which implicitly guides the model to produce confident low entropy anchor predictions. For training objective, we penalize when the anchor prediction PIM is different from the target. This is the target, plus is the target, and this one is the anchor prediction. And of course, we also add H, which is this average H of P bar, because it's an entropy of P bar. So we just regularize to maximize this entropy, or we minimize the negative entropy of this one. So the overall objective to be minimized when the training encoder parameter theta. So this one is just a cross entropy between what is Pi plus and what is prediction. And this lambda is just a hyperparameter that controls the weight of the regularization.